Hello everyone, this is Mr. Tickner and this is the solutions for paper 2 from the Year 11 mock, and it should be a slightly shorter one than last time. Okay, so so question 1. Okay, we've got a bit of a multi-choice one. Energy is transferred when the filament lamp is connected to a battery. Which method of energy transfer takes place between the battery and the lamp? There is only one answer there, which is electrical. Okay, so we've got electrical. And then which method of energy transfer takes place between the lamp and the surroundings? Well, that is light. So it is A for electrical, B light radiation. Okay, then we have question 2. We've got a builder needs to lift a large stone block. Diagram shows the stone block. Draw an X on the diagram at the center of gravity of the stone block. So this is the weight. The center of gravity is the point through which all the weight acts, and the weight will start to act in the center of gravity. So you're looking here really to be marking something around about there. Okay, so you're allowed a little bit of leeway, but it says your X had to be at the top of the weight. So weight acts from and through the center of gravity. So it's a point around there. We've got the mass of the stone block is 130 kilograms. Capital weight of the block, well, we're using here weight equals mass times gravity. So we've got essentially mass of 130 times 10. So we've got 1,300 newtons. Okay, so 1,300. That number will come up again. Come up here. Okay. So a builder is using so we've got a moments problem here. We've got a builder using a wooden plank to lift a large stone block. The plank is uniform and pivoted at the center. As they're holding it balanced, so state the principle of moments. So there are 2 marks here. So there's 2 things you kind of need to say. The first thing is that when balanced, okay, or in equilibrium. Okay, that's the first mark. So something idea that this is an extension when balanced or in equilibrium, you get your clockwise moment is equal to your anti-clockwise moment. So basically, we're saying that the moment from this thing going this way and the moment from this force this way, they will be, if they are equal, then you've got a situation which is balanced. The builder is pushing down with a force of 520 newtons to keep the plank horizontal. Calculate the distance x. So we want to know what the distance is, what the distance x is. So we're after this one here. So we have to use the principle of moments. The clockwise moment equals the anti-clockwise moment. So what we're going to get here, essentially we need to say that the anti-clockwise moment, which is this one, is this distance multiplied by the weight. And the weight you have just worked out in the previous part of the question. So what you've got here is that 1,300 times 0.3, that's going one way, and that's got to equal our thing going in the other direction, okay, which is this force of 520 times by this distance x, so equals 520 times our unknown distance. Okay, so you get a mark for either expression of these. So if I saw these run, you get a mark correctly saying I'm going to equate one to the other and then working it out. So we get a distance x. So x is equal to 1,300 times 0.3 over 520, and that comes out as being 0.75 meters. Therefore, calculate the length of the plank. Well, if you know that this distance is half the distance, so you know this is half the actual distance of the plank, you just take this number and multiply by 2, which gets you 1.5. If you got this number wrong, you still get an arrow carried forward. So whatever your answer is here, if you take this answer and times it by 2, that looks like I'm doing that thread, and put that number in there, you get the mark for that. That's all completely allowable. Right. Then got a question on momentum. So, curling is a sport played on ice. A player slides a stone across a stone across ice towards the scoring zone. The ice reduces friction, so there is negligible friction. Okay. Show that momentum of the stone is approximately 50 kilogram meters per second. So the first thing is that you're selecting momentum equals mass times velocity. And so what we are doing here is mass of 17 times 2.9, and we get 17, we get 49.3, which is approximately equal to 50 kilogram meters per second. Cool. The stone slides towards the scoring zone. In the scoring zone, it collides with another one. After the collision, both stones move in the same direction as the initial stone. The velocity of stone A after is 0.4. Calculate the velocity of stone B after the collision. So here we've got to use the conservation of momentum. Okay, so we need to use the idea that momentum before is equal to momentum after. So we're going to get a mark for talking about that. So our initial momentum is equal to 50 kilogram meters per second. Okay, so that's the initial momentum, and that's got to equal the final. So we've got to therefore, let's, I don't know which one it is, but we've got stone, oh that's stone B and that's stone A, say it's coming from this direction. And that will have to equal the momentum of A at the end plus the momentum B at the end. So we know what these two things are. We now need to work them out individually. So we know the velocity of stone A after the collision is 0.4. So we know that momentum of A is now mass, which hasn't changed, which is, let's check that I'm remembering that one, 17. So we've got 17 times 0.4, okay, which is 6.8. And then we've got, so therefore, what we can therefore look at is the momentum of B afterwards is going to be 50 minus 6.8, which is 43.2. So we've got, that's our momentum of B. And we know that that equals the mass of B times the speed of B. That equals 19 times the velocity of B, and so we have 43.2 over 19. Okay, and that gives us, so we end up with 43.2 over 19, and that gives us 2.3 meters per second. Okay, so there's a mark there for knowing that using the concept of momentum, calculating the momentum of A, working out therefore, so basically this gives you a mark, this gives you a mark, this gives you a mark, and then this gives you a mark. When the stones collided, they were in contact for a time of 25 milliseconds. Calculate the magnitude of the force exerted, A exerted on B during this collision. So what we need to do here, we first need to say we've got 25 milliseconds is equal to 25 over 1,000 seconds. So we've got 0.025. Okay, so that is going to be what marked. We've got to do a conversion out of milliseconds. And then we are using force is equal to the change in P, the change in momentum over the time. So we've got a change of 43.2, we've got a time of 0.025, so we end up with 43.2 over 0.025, and that gives us 1,700 newtons. Okay, we've got metalworker, question 4. Metalworker uses a hammer of a mass 1.8 kilograms to form a piece of metal on an anvil. Calculate the increase in the hammer's GPE when the hammer is raised through a height of 0.95. And so they've actually given you the equation here, which is nice. So we've got GP equals mass times gravitational strength times height. So that is we've got a mass. So we've got 1.8 times 10 times the height of 0.95. And we get about 17 or 16.8 joules, so it's about 17 joules. The metal worker moves the hammer down to strike the metal. The hammer must have at least 21 joules of energy in its kinetic energy store as it hits the metal. To deform it, explain why the metal worker must do at least 4 joules of mechanical work on the hammer to deform the metal. So basically, what we need is that if you convert all the GPE, so you need to if all GPE goes to KE, so let's say you drop it, all of it goes to it, therefore that will mean that kinetic energy equals 17 joules. So you just drop it, you're only going to get 17 joules, therefore 4 joules more work needs to be done. Okay, and you can mathematically say that by saying that the kinetic energy that you need is equal to the GPE that you would get plus the work that you would actually do. So you need to do, to get to 21, you need 17 plus 4. So just the idea of making sure you know the conservation of energy. Okay, calculate the kinetic velocity of the hammer just before it strikes the metal, and we're going to take the kinetic energy as being 21 joules. So we need to say that kinetic energy equals a half times mass times velocity squared. And so put those substitutions in, so we get 21 is 0.5 times 1.8 times v squared. I'm just going to go over here and type it right, it's something big. So got 21 divided by 0.5 is minus 42. So we get 42 over 1.8, sorry. Square rooted is going to equal b. And that comes out as being 4.8. You could also say 0.5 times 1.8 is 0.9. You get the square root of 21 over 0.9. Any kind of rearrangement of that is fine. Okay, so then we move on. Number 5, aircraft travel along a runway. The aircraft starts from rest as a constant acceleration of 4 kilometers per second squared. Calculate the distance required to reach a takeoff speed of 75 meters per second. So the equation that we want here, we need a final speed. We know it's got an initial speed. We need a final speed. We've got an acceleration. So we're going to use v squared equals u squared plus 2as. Putting in what we know that v has got to equal 75 squared is equal to u is 0, so that's nice. 2 times 4.1 times s. So we get 75 squared over 2 times 4.1 is 8.2 is equal to our distance. And that comes out as being around about 686 meters. Or about 690 meters. The aircraft takes off, reaches its maximum height above the ground. At maximum height, the background radiation count rate is higher than the on the ground. Explain what is meant by background radiation. So, background radiation, your ideas is your first marking point is an idea that it is it's radiation that is always present. So wherever you are, there is background radiation, stuff that's always present. You can get a second mark in their marks by saying that there is no obvious source. Okay, so you can clearly say that there's no they come from a multitude of sources. That's a bit of a weird one to say. I'd much prefer getting this. The third marking what they say is like giving a named source, so saying where it might come from. And your big ones are things like, giving a source. So things like radon, rocks, cosmic rays, etc. So anything else, anything that's a named reasonable source, get a mark for that. Okay, that we didn't do. Number 6, nearly there. A student does an investigation to determine the temperature time graph of water as it changes state from ice to liquid water. The ice is an initial temperature of -17. After 5 minutes, it begins to melt. After further 6 minutes, all the ice is melted. Sketch a graph on the axis to show how the temperature changes with time. Assume that the rate of energy transfer is constant. Okay, so we've got, 3 marks we've got for this one? So let's think about that we're going to do. So we have no scale along this axis, and they've given us some time. So they've got a 20-minute time, they've got 6 minutes, and they've got 5 minutes. Okay, so they're doing a whole thing for a certain amount of time. Just check there and get that right. So let's go up. Let's say up here, we're going to get to 20. So I'm going to try and do this in like, so 2, 4, 6, 8, 10, 12, 14, 16, 18. Let's go 20 there. Okay. So something, drawing a reasonable scale. And that's 20 there. So we're going to start at -17, and after 5 minutes, we are going to get all the ice is melted. So after 5 minutes, the ice begins to melt. So after 5 minutes, okay, so there, we're going to have a straight line. We're going to increase the temperature to here, okay, because whilst until the ice begins to melt, so while it's all ice, you will get just a steady change in temperature. Okay, so during this period, okay, we are getting an increase in temperature until we get to melting point, which is 0 degrees. We get a further 6 minutes, so we've got 5, 2, 4, 6 minutes, so we're going to get to 11 minutes, which is there, and we're going to go on a straight line. Okay, and the investigation continues for 20 minutes. So then we're going to get some kind of other line that's doing, say, this. Okay, so we're going to get some kind of line there. Okay, and so that is, that's kind of what we're after. Okay, so there is a mark for this first bit here, that you've got something that rises steadily here, and that would be, you've got to label up all these things, so 2, 4, 6, 8, 10, 12, 14, 18, and 20. So you get a mark for that, and then you get temperature of 0 for 5 minutes, and then you have it there. Okay, so that's our 3 marks. Suggest a precaution the student should take to obtain high quality data. So sort of precaution, so various precautions that we want to make here. This isn't about accuracy or precision, it's just something that would mean that our data wouldn't sort of like get. So we've got a lid, okay, keep the lid on, that's probably a good thing. Keeping the heater submerged, so making sure it's always underwater, that's another sort of thing to do. You've got a thermometer, and remember your thermometer's over here, but your heater's here, so stirring. Okay, once the ice is starting to melt, you've got a liquid, so stirring the liquid would be a good thing. And then just because they are very generous, they will allow you to get the idea of repeating and averaging, which is nice. So any kind of there's a lot of things you can say. So make sure the heater is submerged. So stirring. They are allowing, keep lid on, which is a bit weird. or repeat and average. Okay, so the two most obvious ones here, I think, are this one, because anytime you've got something where you're measuring the temperature of a liquid, you should always stir it. And then this one, which is good practical sort of like skills anyway. During an experiment, the heater transfers 2,500 joules of energy. We've got a specific heat capacity of 880 joules per kilogram degree Celsius. We've got a mass of 48 grams. Oh, that's exciting. We've got to make sure we do a conversion out of that. So we are using the equation, it's written in the book as change in thermal energy, which is a Q, equals mc change in temperature. Seem to have gone from blue to red, so I'm going back to blue. So what we have here is 2,500 is equal to 48 grams. Well, that's 48 over 1,000 times 880 times the increase in temperature. Nicely here, we are only interested in what the increase in temperature. Because we're just dealing with the beaker. Okay, so we end up with substituting in. You can rearrange it, and you end up with a change in temperature of 59 degrees Celsius. Okay, so you just rearrange all those things. And then on to the final question. A student investigates the speed of sound in air. So we've got a microphone, we've got a second microphone, we've got a data logger. Microphone's sound is made to the left. The data logger records the time when the sound wave reaches each microphone. The student uses the data to calculate the time taken for the sound wave to travel from A to B. Okay, so describe how the student could determine the speed of sound in air using his calculated value of the time taken. Okay, so first off is therefore, so if you've got a time, so the sound wave has sort of like, come in, sound waves come in, sets off a line here, and then it travels its distance here. So we're basically, one is we need to measure the distance from A to B. So we need to know the distance from A to B. Second thing that we therefore need to do is to say an instrument. So we'd say we're going to use that with tape measure or meter ruler. And then 3, we've got a time, we've got a distance. We then use speed equals distance over time. Suggest why the student does not use a stop clock. Is that basically the time is too small. Okay, so this is beyond the human ability to say start and stop. Just for reference, I mean, speed of sound is about 330 odd meters per second. So if you had these two microphones 330 meters apart, there would still only be a second between this measurement and this measurement. So anything that's in a lab, it's absolutely impossible to do. You wouldn't be able to detect the measurements. Right, the student investigates how the speed of sound varies with temperature. He places several Bunsen burners in the spaces. He lights all the Bunsen burner on a low heating flame. Measure the air temperature in 3 places using 3 temperature sensors. Use the data log to record the time taken for a sound wave to travel. Determine the speed of sound. The student repeats this method as the air temperature increases. Suggest why it is important for all the Bunsen burners to burn the same amount of gas each second. Well, that would ensure, so for example, if this one was like burning more, then this area would be hotter. We want the temperature to be the same. We want the temperature to be the same at all points. So we want a constant temperature between the microphones. So any kind of you're saying that I need this temperature to not change. Okay, then we have table shows the student's results. Calculate the mean temperature for the last row in the table. Give your answer to a suitable number of decimal places. So correctly calculated. you have what? So 59.8, 61.5, 58.6. The average of that comes out, I believe, of being 59.97. But you want this to a suitable number of decimal places. These are all to one decimal place, so you would end up with 60.0 is the number you need to get. If you say 59.97, you've got too many single figures, you'll get 1 mark. If you accidentally round that to 59.9, you also get 1 mark. So it's 1 mark for calculating the average, so 1, 2, 3 divided by 3. The second is for saying, well, that's to 1 decimal place is to 60.0. Right, okay, so student plots his results, draws a line to it, draw a circle around the anomalous result. Hello, you are not on the line, you are an anomaly. State how the student should deal with the anomalous result. Basically, if you've got an anomalous result, you've got 2 options. One, the most sensible one, is repeat that value. Okay. 2 is that you discard it. Okay. If you've got something that's clearly wrong, you don't then factor it into your calculations. So, if you've got and that's why if you take enough bits of data, this can be important. Explain why a line graph is the correct type of graph. So you had a question like this. So basically, what we've got here is that both variables are continuous. Okay, so and that is which is what line graphs are for that. Okay, so you can have your range. So if we look at the thing here, we're going up 20 to 70, and we're going up 33, 43, 70. So we are changing this, and there can be all the points in between. So it's continuous data. Describe the relationship. So first is first thing that you can get is the relationship is linear. Okay, it's a straight line. Second point is for saying what's that showing is that as temperature increases, speed increases. Okay, and there you go. And that was the entire thing. Just so you're aware here, linear, not proportional. Okay, proportional means something's going to go through the origin. Linear, this is not going to go. This is not going through the origin. Yeah, because 0 is here, and it's not going to get. It's not going to go through 0, 0, because to get to 0, which is about there, you'll be down here. But 0 is all the way down this way. So 0 is down about here. So it's not going to go through the origin. So therefore, it's not a proportional relationship. Okay, and that was the second paper.